Hello and welcome back. This is Jonathan Gardner covering Schroeder's An Introduction to Thermal Physics, and this is section 2.6, which is probably one of the more exciting sections you're going to see in thermodynamics. This is the chapter that explains what entropy is, how entropy works, and kind of gives you a broad overview of what this thing called entropy is. One of the reasons why entropy is so mysterious to the layperson, the person who hasn't really gone through one of these courses and studied it in detail, is because it is not a simple concept. So we've spent the last 5 sections building up to this idea. The general rule that we've discovered as we started counting macro states and running probabilities is this statement here that he has in the book. Any large system and equilibrium will be found in the macro state with the greatest multiplicity. And there's a little side note, aside from fluctuations that are normally too small to measure. So the idea is that when you start using large numbers of things, the highest probability becomes the only probability. And so a general statement of the second law of thermodynamics, and if you go to Wikipedia, you'll see like 6 or 7 different statements about the entropy of what it is and what the second law is. This is the statement that I want you to consider that is the second law of thermodynamics. And the statement is multiplicity tends to increase. Now, in physics, we have fundamental laws. And if you ask for an explanation of why a fundamental law is the way it is, the only explanation you can ever really get that is totally not satisfying is the explanation that that just is the way it is, right? Why does charge exist? Why does mass exist? These things do exist. They just are. Second law is not a fundamental law in the same way that these other things are. There is an explanation of why the second law is the way it is, which is actually a somewhat simple explanation compared to some of the other explanations you might see in physics. And the explanation is simply that the multiplicity increases, right? Multiplicity tends to increase, that the probability after a certain while you're going to arrive at the most probable state, right? That's a general statement that can be like boiled down to these more fundamental assumptions that there is some kind of random motion, that energy is in packets and things like this, okay? The temptation is that since we have an explanation for the seemingly fundamental concept of the second law, that there must be an explanation for the first law and for these other things. The trap is that there aren't. These are just things that are because that's the way they are. We don't really have an explanation of why they are. There's no more fundamental explanation about these things. So the second law is not really a fundamental law, but we're going to treat it like a fundamental law. But don't let that get you confused about what I mean by fundamental. There is no explanation for these fundamental things. Now, we've already seen that we talk about large numbers and large things. And we saw in the last section that large doesn't have to be that big of a number to be large enough for this property to emerge. Even 100 particles in an ideal gas was enough to see this property emerge where it's going to tend towards the most probable state with some immeasurable difference, fluctuations in the differences, right? So this is such a fundamental thing. It happens at even small scales, what you might think is microscopic, like 100 atoms. Really, that's a ridiculously small amount of material. But anyway, it arises for large systems, and the rule is that S, the entropy, is defined to be Boltzmann's constant, K, times the log of the multiplicity omega, right? And so for any large system, it has this property S, entropy, that is the log of the multiplicity times Boltzmann's constant. Now, why is Boltzmann's constant there? Well, in the early days of thermodynamics, they were investigating where the energy was going, and fairly early on, they discovered that when you count all the energy and you dot your I's and cross your T's, some of the energy ends up in an irrecoverable or an irredeemable state, right? And because that energy seemed to sit on the inside of the thing, it's called like the inside energy, the entropy, right? And the energy had units that they could measure, and they used this number to measure it. Now, this came much later. This is Boltzmann and Maxwell, and I think Gibbs were doing work to bring this to light. Statistical mechanics, that matter isn't just like a smudge of peanut butter that you can like infinitely, make it thinner or thick or whatever, but it's actually made of particles. You can count the particles, and the particles have specific behaviors, and they have specific energies. So we take a logarithm of the multiplicity, and that gives us the entropy. And if we're worried about units, we can throw in a K, okay? The units is of K is joules per degree Kelvin, or joules per Kelvin, right? The work per change in temperature, right? How much work is done with every change in the temperature? Typically entropy changes when the temperature itself changes, right? So let's play with entropy now, and we're going to look at the Einstein solid, right? Remember that in the Einstein solid we had omega is equal to EQ over N to the nth power, right? That was the approximation we arrived at. That was very good. And so when we take the log of that, we're going to get the entropy for an Einstein solid is K times the log of omega, which is just going to be K times N times the log of EQ over N. And we simplify this down to, we're going to use, so this is just equal to K times N times the log of E plus the log of Q over N. And this is just 1, so it's just, that's multiplied together. And then we get Kn times 1 plus the log of Q over N, okay? And if we plug in some typical numbers, we'll just use K, so K is 1.381 times 10 to the minus 23rd joules per Kelvin. We're going to use N is equal to 10 to the 22, so we have something less than Avogadro's number. And we're going to use the number of energy packets is 10 to the 24, because it has to be larger than N for this equation to arrive at all. And so we plug all those numbers in, and we'll get something like 0.77 joules per Kelvin for an Einstein solid of that property. Okay. Generally, when you have entropy of a system, of any system, typically as the energy, Q or U, as that goes up, S also increases. And as N goes up, S will increase, right? So as the number of particles goes up, you're going to see the entropy increase. And as the number of energy packets or the total energy in the system increases, the entropy is also going to increase. This arises because logarithm is as the numbers inside of the logarithm increases, the logarithm also increases, right? So it strictly moves up together. And the reason why these affect the multiplicity, well, we've already learned that the multiplicity is basically how many ways can you take Q energy packets and arrange it among, 3n or n degrees of freedom, right? There is the concept that you might hear people, even physicists, talk about this. They'll say that it has something to do with disorder, okay? And this isn't strictly incorrect. It's more correct than incorrect, I would guess. The issue with this is that the intuition behind disorder is sometimes wrong, right? So obviously, if you had a deck of cards, you shuffle it, then disorder is increasing, and also the entropy is increasing, right? Because it's more likely to find the deck of cards that's been shuffled in some kind of random state rather than to see it in some kind of ordered state, right? The problem arises when you have something like, let's say you had a cup of ice. So you had a cup of crushed ice, right? And so we have crushed ice all in here, right? And then we watch that as it absorbs heat and melts in order to become pure water, just liquid water, right? And you might think that the liquid water is more uniform and less disordered than the crushed ice, right? But you'd be wrong. In truth, the liquid water is more disorganized because the energy is distributed more in more possible combinations than it would have been if it was ice. So that's where the problem with disorder arises, is that it's not necessarily intuitive what things are more disordered than other things, right? So if you want to be a physicist, if you want to think like a physicist, you have to get rid of this idea that entropy represents disorder. Not because it's a bad idea, but because it sometimes leads to the wrong intuition, right? Entropy is the logarithm basically of the number of ways you can order the energy in the system, okay? The next topic to think about is how entropy composes, right? So we've already have pressure, volume, the number of particles, the temperature, right? PV equals nRT or nKT or whatever way you want to look at that. Okay, so P, as the pressure, so if you have two systems of some pressure and you connect them together, right? Then the new pressure is, the P final is going to be basically the average of the two pressures, right? it's going to be some combination of those two pressures. It's not going to be a sum of the two pressures. If you have two volumes, so you have V1 and you have V2, and you combine them, then the final volume is just the sum of those two volumes, right? The total volume of the system increases. If you have a number of particles, you have N1 in this system and you connect it to N2 of that system, well, now the final number of particles is just equal to the sum of those two particles. And temperature like pressure, so you have T1, you connect it to T2, then the T final is going to be some kind of average, right? So these numbers, they combine in different ways. How does entropy combine? What happens if you, for entropy, you have S1 and you combine that with a system with S2? What is the final entropy? Okay. With entropy, it's not an obvious answer. Sometimes the final entropy will just be the sum of the two entropies, right? This is, if you think of it like multiplicity, so you have multiplicity of this side and multiplicity of this side, when you combine them together, the total multiplicity is going to be the product of these two in certain cases, right? In other cases, you'll have different things that'll happen, right? So sometimes entropy adds, sometimes it doesn't quite add, sometimes there's a little bit of an error introduced there, right? And we're going to talk a little bit about that in a moment here when we talk about the entropy of mixing, okay? The general rule of thumb, though, and this is the second law in a more definitive tone, I guess, is that any large system in equilibrium will be found in the macro state with the greatest entropy, aside from deviations which are too small to measure, right? In other words, entropy over time always increases. It always heads towards the maximum entropy, right? So entropy basically describes this property that systems will tend towards the maximum multiplicity, right? The question arises, can entropy decrease? Is there a possibility where we can take a system and without drawing entropy out of it, can we decrease the entropy of the system, right? And from some naive sense, you can say like, well, yeah, that makes sense. If I have a table full of coins and I toss all the coins on the table, then it should be possible to go through and make them all heads or make them all tails or something like that, which would result in a state that is most definitely not a higher entropy than it was before. And so entropy decreased in that position, right? The reality is that this is not, it takes energy, it takes thought, it takes calories, you're burning calories to flip those coins, you're doing some kind of work, right? There's some kind of resistance as well happening. And so the reality is that entropy isn't quite decreasing, but the total energy is in fact increasing, right? Now, Maxwell came up with this thought experiment where he said, what happens if we take this being, right, at microscopic scales, right? And he sits there at a gate between two volumes of gas, let's say, right? And if he sees a fast molecule approaching, he opens or closes the chamber such that the fast molecule stays on one side. And if he sees a slow molecule approaching, he opens or closes it such that the slow molecule remains on the other side, right? And in this case, it seems like we found a system where we can actually reduce entropy without doing any work, because that little being itself is just sliding a door open and closed, which has no net effect on the total energy, right? And there's no friction at the scale as well, so it should be perfectly fine, right? This is one of those questions that has plagued physicists. How do we resolve this paradox of Maxwell's, what they call Maxwell's Daemon, right? How do we resolve this paradox? And there's been significant research. Back in the 90s, I remember somebody published a paper, I forget what it was, and this is why I'm not a real physicist. I just pretend to be one on YouTube. But he was able to show that just to do the computation itself, just to do a simple computation at the rate that it needs to be done would produce more heat than you'd be producing, right? So there would be no savings from this machine if you could create it at the microscopic scale, right? So the verdict is that not even Maxwell's small Daemon can violate the second law of thermodynamics. All right, we have some problems here at this point. Problem 228 is to take a deck of 52 playing cards and figure out how many ways you can arrange that, right? And he's talking about the order of the deck. He's not talking about flipping the cards up or down or anything like that, right? And then to figure out, like, if you were to do this over a long period of time, how many different states, how many different macro states could you arrive at? Could you arrive at one where the hearts come first, where it's like all hearts and diamonds on one side and all clubs and spades on the other side or something like that? So you can look at that and figure out kind of what the tendency of that system is if you keep shuffling the deck, 229 is to take two Einstein solids with a different number of particles, right? And then to calculate the entropy of the most likely macro state, okay? And to compare that with the entropy of the least likely macro state. So find the greatest and least values for the counts of microstates in each macro state where the energy is distributed between the two systems, okay? And what is the entropy of that system with just 500 particles total? What is the total entropy in the least and greatest macro states, right? Next one is problem 230. Consider the system of two large identical Einstein solids that you saw in 222. 222 is back in previous sections, obviously. The question arises, what is the entropy of all possible microstates? What is the entropy of the most likely macrostate? And what is the time scale that you'd arrive at these large macro states or whatever? Then problem D of problem 230, subproblem D. So if you were to insert a partition between the solids so that they can no longer exchange energy, right? Would you be able to violate the second law? Is that something that we should worry about? Is it in the grand scheme of things, is this something that we can exploit to reduce entropy? Like, can we just keep partitioning the solids? So that is the first part of section 2.5, continuing, or 2.6. Continuing on, entropy of an ideal gas. So the formula for the entropy of an ideal gas is called the Sacker-Tetrode equation, and it's given by this complicated mess. So S is equal to N times K, and then it's times the log of V over N times 4 pi mu, U is the internal energy related to the temperature, over 3NH cubed, that's Planck's constant, and this is to the 3 halves, okay? And then we're going to add 5 halves at the end. Okay, on my website, I actually derived this formula, partially because I wanted to make sure that I understood what I'm talking about here, where these numbers came, but it turns out this is actually a homework problem, so I won't derive this equation for you, the Sacker-Tetrode equation. This is called the Sacker-Tetrode equation. So we'll refer back to that a couple times. And if you were to plug in some numbers, so a mole of helium at room temperature and atmospheric pressure, and you had a volume of 0.025 meters cubed, and you set it to a temperature, room temperature, you get about 3,700 joules for the internal energy. And I worked this out on the website as well. It took me 3 or 4 goes to get it all right, but you get the entropy is about equal to 126 joules per Kelvin, right? And if you compare that with the entropy you had for the Einstein solid, this is a very much larger amount of entropy in a gas than a solid. And you can think about why that is. If you are to ask, what happens when we increase the volume? Well, if you increase the volume, that number gets bigger, and so the entropy should increase. What happens when you increase the count of particles in the gas? This is interesting because we have a factor of n down here and n down here as well, but this is n to the 3 halves. And so we basically have minus 3 log of n. So does n grow faster than the log of n? The answer is yes, it does. And so the entropy will increase. What happens when the energy increases? Well, that's on the top there, so the entropy is also increasing. Okay, and so we can see that as you add these things, it makes sense, the entropy does increase. An interesting question is, how much does the entropy increase? Well, if we were to count the change in the entropy by changing the volume, right? And so this is going to be nk times, this is a mess, log of the final volume over n times 4 pi m capital U over 3nh cubed to the 3 halves plus 5 halves. And this is minus nk times log of the initial volume divided by n times 4 pi mu over 3nh cubed to the 3 halves plus 5 halves. Okay, and so if we subtract these two from each other, these 5 halves will cancel out, or the nk 5 halves, and then we're left with basically nk, and then we're going to have the log of this divided by that, right? And so the only difference between these two things is Vf, okay? And so that's the formula for the change in entropy when you're changing the volume. Okay. The interesting thing about this is that this applies if you keep the internal energy the same and the number of particles the same. So this is a quasi-static increase of the volume. So as the volume increases, in order to keep the internal energy the same, the temperature basically the same, you have to add heat energy, right? And so this leads to the intuition that basically heat creates entropy. In fact, putting heat into a system always increases its entropy. And we'll talk about this more in chapter 3, he says. Okay, what happens if we didn't actually do any work? We actually had a chamber here with a membrane where all the gas is on one side, and then we puncture that membrane and the volume doubles, right? Well, in this case, the change in the internal energy is the heat being added plus the work being done. Well, how much heat is being added? Well, this happens rapidly, so there's no time for the heat to be added. And how much work is being done? Well, it's not pushing against anything, so the internal energy doesn't change at all, right? But we still find that the entropy will increase by this amount, right? So basically log 2 is the factor of the NK that we're going to see an increase in the entropy, right? And so this observation says there's something about volume itself, which, you know, we went back to the last section. If you go back to the last section and look at it, you'll see that this is due to the fact that if you have a larger space, you have more quantum positions that the particles can occupy. You're basically increasing the degrees of freedom in some way, okay? So this increase in entropy isn't because we're just adding heat as we gradually increase the volume and maintain the internal temperature. It's also the case that it increases just from nothing at all. Like vacuum itself can create entropy. So this is a pretty interesting observation. Entropy has to do not just with energy, but it also has to do with things that you can create out of thin air, like more volume and stuff like that. Problem 231. Derive the Sackur-Tetrode equation. That's a lot of fun for me. It took a while. 232, find an expression for the entropy of the two-dimensional ideal gas in 226. Okay, and so go back to 226, which is back in the last section, and calculate the entropy of that. The two-dimensional ideal gas. We did the three-dimensional here. Problem 233 uses Sackur-Tetrode equation to calculate the entropy of a mole of argon gas at room temperature and atmospheric pressure. Why is the entropy greater than that of a mole of helium under the same conditions? So the difference between argon and helium is argon has a greater mass. That's it. Why did the entropy increase? That's something you have to think about. You might have to think at a quantum level to really understand what's going on there. 234. Show that during the quasi-static isothermal expansion of a monatomic ideal gas, the change in entropy is related to the heat input Q by the simple formula delta S equals Q over T. So this formula is going to arrive again and again. Okay, that's why we have work per temperature as the units that we want our entropy to be in. So show that this is true for an ideal gas. When you add heat to an ideal gas, show that the entropy is going to increase by that amount. And this is actually a general formula that's going to be used again and again in any quasi-static process. We'll talk about that in the next chapter. According to the Sackur-Tetrode equation, this is problem 235, the entropy of a monatomic ideal gas can become negative when its temperature and hence its energy is sufficiently low. Of course, this is absurd. How do you get negative entropy? It doesn't make any sense. So the conclusion is that the Sackur-Tetrode equation must be invalid at very low temperatures. Okay, and so use the example of helium at room temperature and atmospheric pressure. Lower the temperature, holding the density fixed. Pretend that helium remains a gas and does not liquefy. Below what temperatures would the Sackur-Tetrode equation predict that S is negative? Okay, and we're going to talk about cold things in chapter 7. Okay, problem 236. For either a monatomic ideal gas or a high temperature Einstein solid, the entropy is given by NK times some logarithm. And in this problem, what he says is you can basically drop the logarithm. That's going to be some, some small factor. It could be like, some small number or large number, but it's going to be a number, right? Even with these, I want to say beyond astronomical numbers that we have inside of here, the logarithm comes out to like something like, 120 something, right? And so like this is basically the multiplicity is e to the 120 something, which is a fantastically large number. and you take the logarithm, and you just get 120, right? And so he says, what happens if we just say, hey, the entropy is, it's all proportional, it's roughly N times Boltzmann's constant, right? And so go through and you can calculate a bunch of entropies of things. And you'll see that you're actually pretty close. You're not too far off with the entropy there. At this point, I want to introduce a concept that leads to a paradox that is not yet resolved. We still don't know what the resolution of this. This is the entropy of mixing, right? So we can create entropy by increasing the number of particles, we can increase the volume, we can increase the energy, but there's something else we can do that creates entropy, and that is to mix two different materials, like let's say helium and argon, and if we mix those together, that will actually create entropy. And to show you that it's not just the entropy that you would have gotten if you mixed helium with helium, but it's actually some new entropy, we're going to calculate how much entropy they have. And the way we're going to do this is we're going to look at the left side and then calculate what happens after it's allowed to mix. We're going to look at the right side and calculate what happens after it's allowed to mix. We're going to pretend that the other substance doesn't exist, right? And so on the left side, let's say S of A, the change in that S of A is just going to be N times K times a log of the final volume over the initial volume, right? And since we're doubling the volume, we're going to have NK log of 2. And indeed, the change on the other side is going to be the same thing, NK log of 2, right? So we have chamber divided in half, we have helium on this side, we have argon on that side. So both sides, when we remove the partition between both sides, we will see the increase of entropy to be 2, the total change in entropy will be 2NK log of 2, okay? This is called the entropy of mixing. Okay? This only applies when we have different substances mixing together. If we were mixing helium with helium, we wouldn't see this increase of entropy, right? You can calculate for yourself what you should have gotten if you just mixed two chambers of helium together. So basically what we're doing is we have S equals NK log of, NK times a log. I'm sorry, the log goes on the inside of the parentheses, of the volume over the number of particles. We have 4 pi m u over n, 3n h to the cubed to the third, and that's 3 halves plus 5 halves. Okay, so if we were to take helium and mix it with helium, then the volume would increase and the number of particles would increase. And so we would get the change in S would basically be S of n comma v plus S of n comma v for both sides, minus S of 2n with twice the volume, right? Now, the 2 in this top and the 2 in this bottom will cancel. There will be a 2 here, but this is 3 halves of that, right? So it's, you know, the square root of 8, 2 root of 2, right? And so the log of the 2 root of 2 is tiny. It's infinitesimal compared to these other numbers, right? So we could actually drop that, and the change in entropy here will actually be 0. Removing the partition when you have helium on both sides will not change the total entropy, right? And so this entropy here, this is new. It does not arise because you have stuff on both sides, right? So you might be wondering why there's this n in this denominator here. Why is it v over n and not just v, right? Well, if we went back to our ideal gas when we were counting the multiplicity and we said, you know what, we're just going to pretend that we can distinguish the atoms, right? Then there was this factor 1 over n factorial that we had to introduce because it said that we didn't want to double count the states, right? Because they're indistinguishable. It doesn't matter if the first particle's in this state and the second part on that state, or if they're reversed, right? It's the same. Well, if we don't do that, then we will arrive at this weird formula for the entropy. It's going to be Nk times the log of just plain old V times what you're used to seeing, 4 pi m u over 3 n h cubed to the 3 halves plus 5 halves. Right, 3 halves. I'm sorry, 3 halves, not 5 halves. Okay, so if you were to sit down and redo all of the calculations we've done without this factor, this is what you would arrive at. Okay? Now, this is interesting because it says if we simply have the volume, right, then the entropy should decrease, right? So the idea is that under this formula, if we had a tank of helium gas, right, and we just partitioned it off, then we have suddenly decreased the amount of entropy in the entire system. We found a way to basically violate the second law. Okay. Now, we don't count things this way because of this problem. Well, slightly because of this problem, but we don't have a real explanation of why this isn't the right way to do it. And so this is what we call the Gibbs paradox. The math and everything seems reasonable, aside from the fact that we're treating each molecule as distinguishable, which quantum mechanics says you can't. So if the math and everything seems reasonable, aside for this one case that causes a violation of the second law. So we have some more problems. Problem 237. Using the same method as in the text, calculate the entropy of mixing for a system of two monatomic ideal gases, A and B, whose relative proportions are arbitrary, right? So they don't have the same numbers. Let N be the total number of molecules and let X be the fraction of those that are of species B. You should find that you get some formula for the mixing, and you should check that it reduces to the one given in the text when X is 1/2, right? So just do the math for yourself, figure it out. Problem 238, the mixing entropy formula derived in the previous problem actually applies to any ideal gas and to some dense gases, liquids, and solids as well. For the denser systems, we have to assume that the two types of molecules are the same size and the molecules of different types interact with each other in the same way as molecules of the same type. There's the same kind of force and everything like that. Such a system is called an ideal mixture. Explain why for an ideal mixture the mixing entropy is given by this complicated formula here. Is equal to K times a log, and we have N and we have Na. So this is that formula that's, N and A is going to be N factorial over Na factorial times N minus Na factorial. Okay, so that's that formula there. So the binomial, whatever you call it. Use Stirling's approximation to show that this expression is the same as a result of the previous problem with both N and Na are large numbers. Okay, that should be pretty fun. More math. 239. Compute the entropy of a mole of helium at room temperature and atmospheric pressure, pretending that all the atoms are distinguishable, compared to the actual entropy for indistinguishable atoms computed in the text. So just, use this formula and do what we did for helium before. Pretty simple stuff. Okay. So the last part of this video that's already too long and probably boring is talking about reversible versus irreversible processes. So because of the second law, we know that if entropy increases, then this is irreversible. You could somehow extract entropy from that system, but that entropy has to go somewhere, and so you have to increase entropy somewhere else, and so this is an irreversible process. So think like refrigerators. Right? Refrigerators have to be plugged into the wall, right? So even though we're seeing the heat being drawn out of the stuff on the inside of the refrigerator, there is more heat being created somewhere else, more entropy being created somewhere else. Now, if we can keep S flat so it doesn't go up or down, then we could have what we call a reversible process, where we can go backwards and forwards and it doesn't matter. In reality, typically processes are not reversible. There's always something that happens that increases the entropy, okay? But in practice, we can create processes that have very low increases in entropy and treat them as if they were reversible, okay? One type of process that creates new entropy is expansion, sudden expansion. Popping a balloon, for instance, your entropy is going to increase rapidly, okay? And it just creates entropy out of thin air. It doesn't really use anything to create it, right? However, if you have a gradual compression or expansion, then you can keep S flat so it doesn't go up or down. And in chapter 3, we'll talk about this term quasi-static that I brought up earlier. We'll be more specific and definitive about what we mean by that and what kind of processes do that. And we'll find that in these cases, the work done on the system has to be equal to minus times the pressure times the volume change in the system. One thing to think about is why you can have a process that changes the volume but doesn't change the entropy. And thinking quantum mechanically, you can think of it this way. Like if you were to suddenly change the volume, then some of those wave functions inside of the volume would have to shift and increase in their energy. But if you do it gradually, then none of the wave functions will have a great enough increase in energy in order to actually elevate the total energy of the system. And so that's one level of intuition you can get from an understanding of how these things are derived. We almost always think about something that flows heat. So we have a high temperature and a low temperature, and we have some kind of heat flow from the high temperature to the low temperature, right? And this is almost always an increase in entropy, right? However, if the temperatures are very close and it's only a tiny amount of energy flowing from one side to the other, we can occasionally approximate and find that you do have situations where the entropy change is practically zero, right? And so it is possible, in fact, in the micro, when you're looking at very, very tiny infinitesimal changes of things, typically those processes themselves have no change in the entropy, right? However, those processes do add up, and when you add them all up together into like the things that we observe every day in real life, there is most definitely an increase of entropy, okay? And then he closes on this note. So he kind of waxes a little bit philosophical here. There's two things. One is that in the future, at some point in time, entropy will reach a maximum state. And that would be a very boring universe to live in because there's no processes happening, there's no change. It's basically arrived at the maximal disorder, if you want to use that word, which I don't. It's arrived at the maximum multiplicity of the universe. Everything is in a state where it's the most likely state, and there's no chance of anything ever happening interesting ever again. On the other side of the token, the fact that entropy exists points that there must have been a definite beginning of the universe. There must have been a point in time in the past where entropy was very, very low. And what we're watching unfold before our eyes is what happens as the universe approaches the greatest multiplicity. Both of these questions are fun questions to think about. They're very philosophical. They might even be considered religious. They're irrelevant. They really don't matter. Like, we observe this happening in nature. We're able to explain the processes behind it. We're able to quantify it and create predictions around it. And so that's really where you should be focused in your physics. You can talk about, with a philosophy major, about what happens in the distant future or what the universe came from, all these different things. Using your understanding of second law of thermodynamics might guide your discussion of those philosophical discussions. However, those things lie outside the realm of physics, and just don't let those things bother you so much as some people might let them, right? His point is, he says that we have at least 5 billion more years of this sun. We might as well enjoy it, right? Problem 240. For each of the following irreversible processes, explain how you can tell that the total entropy of the universe has increased. So this is a fun little problem, okay? 241, describe a few of your favorite and least favorite irreversible processes. For me, my favorite is eating a good meal, okay? And my least favorite is having a massive car crash, right? You can come up with your own things and describe how the entropy has increased for those processes. And you can think about, maybe you want to spend your entropy that you've been allotted as a distinct being in this universe. You want to spend your entropy doing the things that you would prefer to have rather than the things you don't want to have. So you'll drive more carefully, and you'll learn how to cook for yourself or something like that. Problem 242, a black hole. This one's really interesting. This one gets into Stephen Hawking's conclusion, where he calculated back in 1973 the entropy of a black hole. And the way he guides you, the student, through this process is you're going to basically arrive at the same result, missing a factor of 8 pi squared, but you're going to get, just by dimensional analysis and by just some very basic assumptions, some very broad generalizations, you're going to arrive at the same problem. So I encourage you to go through problem 242 on your own and let that be a fun challenge for yourself. And finally, there's this quote by Richard Feynman. He says, "There are 10 to the 11th stars in the galaxy. That used to be a huge number, but it is only 100 billion. That's less than the national deficit. We used to call them astronomical numbers. Now we should call them economical numbers." So, yeah. The sad thing is the numbers that we're dealing with are much larger than even the national debt and deficit and stuff like that. And I recall there's a movie, Austin Powers, I think it was, where Dr. Evil travels back in time to the 1960s and demands, $1 billion from the federal government. They just laugh at him, because that's an unheard of, ungodly amount of money. Anyway, guys, I hope you enjoyed this. I know this was long, but this should really give you a solid grasp of what entropy is, kind of some ideas and how it works. In the rest of the text, we're going to go over and look at the things that surround entropy. We'll be able to discover more, and we'll be able to get a better grasp of how entropy behaves as we see it in practice. So guys, have a great day. Take care, and bye-bye.